Do you remember when we were learning about scientific notation that I said there are 1 times 10 to the 19th atoms in a single grain of sand? Did you just believe me? How do you know it is true? How do we even know that there is such a thing as atoms?
The idea that matter is made from atoms can be traced back as far as 400 BC, when ancient philosophers pondered the fundamental nature of matter. But philosophers, they were, not scientists. It would be another 2,000 years, the early 1800s, before scientists found experimental evidence that pointed to the existence of the atom. Until then, the idea of the atom was just that, an idea without proof. In this lesson, you will define the terms theory and model, describe the development of the modern atomic theory as a result of the contributions of Democritus, Dalton, Thomson, and Rutherford.
The understanding of the structure of the atom has been a slow, gradual evolutionary process. And even today, we do not fully understand all of the mysteries surrounding the most elemental particles of the universe. Because direct observation of atomic structure is all but impossible, scientists have relied on models to represent the structures of atoms.
For the chemist, models are an important tool. They help us understand the unseen. Today, as you watch students like yourself work to devise an acceptable model of the inside of a black box which their teacher has given them, think about what you already know about models. Models may be visual, verbal, or even mathematical. To be valid, scientific models must explain all known facts, and they must enable the scientist to make correct predictions. Let's watch as these students create their own scientific model during this lab activity.
In this lab, you're going to be given 2 identical boxes, and it's important that you remember, do not open either box at any time. Washers are in the box. They're either attached to the rods or they're simply loose in the bottom of the box. So you're going to make observations by tilting the box back and forth very gently and listening. You're going to predict what the inside of this box looks like, and you're going to draw a model. Then you'll make predictions about what will happen when you pull the rods out. Now, you might find out that your predictions are wrong, but that's okay because that happens to scientists all the time. And what you do is just revise your model. And so you've got a second box for that purpose. So you'll revise your model, you'll draw it, and again make predictions as to what will happen when you remove rod AB and rod CD, and hopefully after a couple of revisions you're going to be satisfied with your model. Just don't open the boxes.
As Lindsay and David work together, they not only listen to the sounds from their box as they gently move it back and forth, but they also feel their box for any vibrations that might lend a clue as to the hidden structure inside. Based on these observations, Lindsay decides that she's ready to construct the first model of her black box. She places a circle representing a washer on rod AB, then places another circle in the box, not attached to a rod, to represent a washer that is simply sliding on the floor. David thinks that an additional washer is on rod CD, and so he places a circle on rod CD to represent this additional washer. Lindsay is now ready to test her model. She slowly pulls AB from the box, listening carefully, but doesn't hear anything drop. She then pulls out rod CD, and a washer fell from rod CD. It's obvious that the student's original model needs revision. Lindsay redraws her model, now without a washer on rod AB, but she keeps the washer on rod CD and the additional washer that is simply sliding on the floor of the black box. The students still need to test the revised model using a second box, which is exactly like the first. David slides the box gently back and forth, then removes rod CD. He hears the soft thunk of a washer falling. Lindsay pulls rod AB from the box, but hears nothing. The students feel confident that their final model of the black box is correct. Now, this is the tough part. The teacher is not going to tell the students if they're correct or not. just like modern scientists have based their model of the atom on experimentation without ever actually seeing inside the atom. The students have based their model of the inside of their box on experimentation without ever actually seeing inside the box.
Now that you've seen how important scientific models are, let's piece together the work and consequential models that led to our modern atomic theory and model of the atom. Today's lesson contains lots of history. Bear with us. So, a model helps us think about a problem and is a necessary first step in the development of a theory. A theory is an explanation of observable facts and phenomena. It is an idea that has stood the test of time. Remember, to remain valid, models and theories must explain all known facts, and they must enable the scientist to make correct predictions. As more information becomes available, models and theories are subject to revision, just as the model of the black box changed as new information was gained. One of the most important theories in chemistry is the atomic theory. Let's see how we progressed from a simple theory developed from thought experiments to our modern atomic theory, which is not simply based on thought, but rather based on experimentation. Have you ever thought about this? I have a thin piece of copper wire here. If I cut this wire in half, and then in half again, and so on, and so on, can I keep going like this forever, getting smaller and smaller pieces of copper, or eventually, will I get a piece of copper that can't be cut anymore? Hard to hold, but can it not be cut? What, you've never thought about this? Well, Greek philosophers didn't have the internet or video games more than 2,000 years ago, so they thought about this problem and hotly debated it. Their debate was the beginning of our atomic theory. Democritus, born in 470 BC, proposed a thought experiment. The reasoning was that if a substance is cut into smaller and smaller pieces, you eventually will have the smallest possible piece that still behaves like the original substance. Democritus called the tiniest piece of that substance an atom. The word atom comes from the Greek word atomos, which means not to cut, or not divisible. Democritus's ideas were quite similar to our own. However, Aristotle, born in 384 BC, did not believe in atoms. He didn't believe that there would ever be a particle of matter that couldn't be divided. The idea of the atom was rejected by Aristotle. Most people sided with Aristotle, and consequently, the belief in atoms was lost for 2,000 years. That's when John Dalton's model of the atom was introduced, reviving the idea that the atom exists. Let's see what Dalton proposed nearly 2,000 years after the idea of the atom had been rejected.
The English chemist John Dalton developed the first model of an atom in 1803. Dalton saw atoms as being indivisible, indestructible spherical particles. He believed that all atoms of the same element were exactly alike in both shape and mass. He also believed that the atoms of different elements were different, each with its own distinct size, shape, and mass. Finally, he believed that compounds were formed by the joining of atoms from two or more elements, and in any compound, the atoms of the different elements present were joined in a definite whole number ratio. Dalton's model explained very well what was known about chemical reactions to that point in scientific history.
So, to review, it wasn't until 18th century Europe that the belief in atoms started to make a comeback. Early chemistry investigators noticed certain characteristics shared by all chemical compounds. Their observations led to 3 laws that describe how compounds are formed: the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. As you saw a few minutes ago, it was during the early 1800s that a schoolmaster named John Dalton proposed an explanation of these 3 laws. His atomic theory is when we see Democritus's idea of the atom become more than an idea. It becomes a theory with experimental backing. Dalton's theory proposed 5 things. 1. Atoms are the building blocks of matter. 2. Atoms are indivisible. 3. Atoms of the same element are identical. Four, atoms of different elements are different. 5. Atoms unite in small whole number ratios to form compounds.
Gosh, this atom stuff is blowing my mind.
For many years, the model of the atom remained indivisible, not to be confused with the word invisible. And presto! In the mid-1800s, let's see what scientists began to discover about subatomic particles and atomic structure. Voila!
The Crookes tube is an ancestor to the modern-day television tube. In experiments conducted by the English scientist J.J. Thomson with this tool, he noticed that a stream of negatively charged particles would flow through the tube no matter what type of gas was used. Thomson postulated that the negatively charged particles were present in the atoms of all elements. Initially, these particles were referred to as cathode ray particles, but today are called electrons. In further theory, Thomson also stated that all atoms were made up of positively and negatively charged particles that were evenly distributed throughout the mass of the atom. Thomson continued, however, to view the atom as a solid mass.
Scientists were beginning to discover even more about the structure of the atom. The first discovery of a subatomic particle was the result of Joseph John Thomson's work with cathode ray tubes. As a result of this work, J.J. Thomson hypothesized that cathode ray particles are fundamental particles that are present in the atoms of all elements. These cathode ray particles are what we now call electrons, and J.J. Thomson is given credit for their discovery. This was a blow to Dalton's model of an indestructible, indivisible atom. Within a few years of the discovery of the electron, the proton was discovered. Thomson postulated that the atom was made up of positive and negative particles that were evenly distributed throughout the mass of the atom. This model became known as the plum pudding model, named after a British dessert of sweetbread with pieces of fruit embedded in it. Although Dalton's indestructible atom was no longer the accepted model, Thomson's model of the atom was still that of a solid mass.
In 1909, the British physicist Lord Rutherford conducted experiments that indicated that atoms largely consist of empty space. By shooting a beam of alpha particles through a gold foil surrounded by a circular-coated fluorescent screen, Lord Rutherford noted that most of the alpha particles seemed to go through the foil screen undeflected. However, some particles were deflected slightly, while still others were deflected at a 90-degree or greater angle. Lord Rutherford interpreted these observations to mean that each atom contained a small, dense, positively charged central portion, or nucleus. He further hypothesized that the positively charged nuclei repelled the positively charged alpha particles, deflecting those that came near, much like a bullet ricocheting off a steel beam. However, because the nuclei were so small relative to the entire size of the atom, not many hits were scored, and most of the alpha particles passed straight through the empty portion of the atoms. Rutherford further asserted that electrons move about in the empty space that makes up most of an atom's volume.
So let's review. Rutherford performed the famous gold foil experiment that provided experimental detail about the atom's structure. Remember that he aimed positively charged alpha particles at a piece of gold foil. Most of the alpha particles went right through the foil. But a few of the particles were deflected. A very few of the particles even bounced back. What a surprise. Rutherford reasoned that each atom in the gold foil contained a small, dense, positively charged nucleus surrounded by electrons, which are contained in mostly empty space. Rutherford suggested that electrons orbit the positively charged nucleus much like planets orbit the sun. So he called his model of the atom the planetary model.
The students think of something they haven't tried yet. They turn the box upside down and shake it. Certainly the students didn't expect a washer to fly out of their black box just because they turned it upside down. Just like Rutherford, if they keep investigating with better techniques and tools, who knows what they'll find out about their black box.
So, we've gone from Democritus's thought experiment that atoms exist in the first place and were indivisible, to Rutherford's planetary model, which viewed the atom much like our solar system, with negative electrons orbiting the positively charged nucleus. The story surely isn't over yet, because it was Rutherford's own student, Niels Bohr, who suggested an alternative to Rutherford's model, when classical physics of the day found a problem with Rutherford's model. We'll save that for another day, though. Now, let's take our chemistry quiz and see how well you understand this material. Write the answers to each of the questions in your notes. Your local teacher will go over the answers with you after I say goodbye. Here goes.
First, let's try cumulative review question number 1. What is it called when a solid turns directly into a gas? A. Melting. B. Boiling. C. Freezing. D. Sublimation. Our second cumulative review question is true or false. When a hypothesis is tested and shown to be incorrect, the experiment is a failure. A. True. B. False.
Okay, now we're ready for question number 1 from today's lesson. The word atom comes from the Greek word atomos, which means A. Divisible, B. Indivisible, C. Invisible. Question number 2. Rutherford performed the famous A. Omega experiment, B. Alpha experiment, C. Gold foil experiment, D. Thought experiment.
Now for question number 3. Rutherford's experiment led us to believe A. Most of the atom is empty space, B. The atom has a dense, positively charged core, C. Neither A nor B, D. Both A and B. Question number 4. Who is credited with the first atomic theory based on experimental evidence? A. Democritus, B. Aristotle, C. Dalton, D. Rutherford. Now, in conclusion, your final quiz question. An explanation of observable facts and phenomena is called A, a law, B, a theory, C, an experiment, D, none of the above.
Hope you did well on our little quiz. Be sure to rest up before we meet again, because we're going to be going on a diving expedition. See you then.